Good afternoon, everyone.
Oh, yeah. Okay.
My pleasure to introduce today's speaker. It's Chris Heckman. Chris is returning to Cornell, and I thought I'd start by just telling you his last few positions, starting with undergraduate, where he went to Berkeley. And in the mechanical engineering department at Berkeley, he worked with one of our graduates, a student of Phil Holmes named Andrew Zeri, and he worked on a problem of the dynamics of bubbles. And then when he came to Cornell in 2008, he continued to work on bubbles. It ended up being a mathematical analysis, including delay aspects. And he did a 4-year PhD. And after that, he went to NRL, where he worked with a guy you may know, Ira Schwartz, on swarms of boats. And did that for 1.5 years. And then went to the University of Colorado Boulder, but he didn't go as an assistant professor. He went as a postdoc, a research postdoc, working with a man named Gabe Sibley. And he did that for 1.5 years, starting 2014. And then his mentor decided to leave and open his own business. And happily, Chris got that position. So now he's an assistant professor at Boulder. And I'm mentioning that to you because many of you are looking for positions, and that's one way to get it. So today he's going to tell us about his research on automatic cars.
Thank you, Richard. So I should say that was not an endorsement to off your advisor, and also my advisor still has a position at the department that I'm in. And so he's currently on leave at a self-driving car startup, which for those of you that work in the autonomy world or robotics, then this is no new thing. I mean, a lot of folks are moving to industry because of the kind of craziness that's happening over there. What we do is we benefit from that because my lab, for instance, has these outside partnerships. So I'm looking forward to talking to you today about some 2 different algorithms that we're developing in my lab that focus on building out autonomy for self-driving vehicles. So robotics today is, well, it's an exciting place to work, as I was just mentioning. One of the things that is happening is that all these big tech companies, many of you may have even internships with them, like Microsoft. They're building out HoloLens. You might not think that that's a robot, but at the same time, the kinds of perception algorithms that are going on HoloLens, the kinds of filters for data on cameras and inertial measurement units for accelerometer and gyroscopic measurements, for instance, those all come from the robotics field or can be used in the robotics field. And other companies, Google, they acquired Boston Dynamics. Now they're selling Boston Dynamics. I'll get to that in a second. Facebook purchasing Oculus, Amazon doing delivery drones, one of the biggest startups, or the biggest startup in history, Uber, focusing on autonomous vehicles. This is clearly a very exciting place to be, just in terms of the market movement. And I want to give a brief overview of 3 major approaches that are sort of being taken in industry, and you'll find that I make industrial connections as often as possible in my talk. So there's this first category in this red box in which there's sort of single-purpose robots, or maybe limited sensing or action robots. They can accomplish a certain task maybe once, or one task repeatably. So for instance, the Roomba, one of the most successful robots to date, is one that people are willing to actually have in their houses, and all it does is clean surfaces. So this is a development from ClearPath. It's basically something that would follow a person in a warehouse, and you can put very heavy objects onto it and not have to carry them. Tesla, for all of Elon Musk's beliefs that AI is going to take over the world and kill all of us, he's willing to employ robots to do basically everything in his factories. and so on. This is Otto, one company that's automizing basically some advanced driver assist for vehicles. So that's category 1. Category 2 is about anthropomorphic types of robots, a kind of robot category that also covers everything from grasping, even though grasping might not necessarily rely on fingers. So very useful, the Baxter robot, a common platform for human-robot interaction experiments, but also maybe not so useful robots, robots that play soccer or something like that, maybe for entertainment. And then there's this third category, which is broadly classed, or I would class it as autonomous vehicles. So obviously in the bottom left corner, here's a picture of Google's self-driving car on a beautiful day, probably the only kind of day that this thing can operate on. And then there's the GoPro. We recently released one of these autonomous quad rotors with a camera on it. It can sort of follow you while you're doing sweet moves on your snowboard, or maybe be able to be used for sentry purposes or border control or anything else. And this is kind of the category that I'm most interested in, as the talk might have suggested. There's obviously a very strong push towards autonomous vehicles, in part because there are so many tasks that we use cars for that don't really necessarily rely on cars. There's this whole idea that we could probably get rid of most urban driving if we just allowed people to have some small robot that would go and pick up some groceries for them, and maybe it's not like an on-demand necessity, that you're not out of milk right now, but you would place an order for milk and it'll arrive sometime in the next 8 hours to 2 days or something. So this is one robot. It's from Starship Technologies, founded by the same people as Skype. Basically, it can go for 3 miles radius around one area. It's pretty impressive, but as you can imagine, driving on the sidewalk and waiting for good weather is kind of different than those on-demand activities, for instance, getting people to work. And so that's just one thing to bring about. And then also, there's these parking considerations. If you've ever thought about what an autonomous vehicle, sort of fleet of autonomous vehicles, how it would change our daily lives, here's a picture of Ithaca and all of the different parking structures that are on Ithaca for which you could pay for using this Park mobile app. And basically every single one of these would likely be unnecessary, or at least all but 5% of them would be unnecessary, because the cars would have far more usability and would constantly be in use. All they would need to do is park at night, essentially, when no one's using them. So some really sad tasks or sad facts about cars in general. I mean, mall parking lots are 20% larger than malls themselves. Most cars are only in use for 5% of the time that they're owned. And frankly, most tasks don't rely on cars at all. And so, obviously, why is there so much research in this on the academic side? Well, at least before people get poached to go to industry. Well, there's a lot of money. DARPA's putting together all these different kinds of programs. For instance, at least on the UAV side, and again, many autonomy packages from UAVs can translate, at least in part, to self-driving ground vehicles. So there's this massive program, $6 million for this competition. There was the DARPA Urban Challenge and a bunch of other self-driving challenges going on. There's specific kinds of hardware that are being developed. For instance, NVIDIA created this cool liquid-cooled GPU that can sit in the back of your trunk and basically do all of these different autonomy tasks in just a very small package, specifically targeting the self-driving car market. Toyota, back last year, dedicated $1 billion towards what they call the Toyota Research Initiative. Some funding, we have part of that funding as well in my lab. And then the federal government is also pushing a lot of money through. So $4 billion to be spent over the next 10 years. The hope is that 25,000 deaths could be avoided just by trying to get people out of the car when they're making less than adequate decisions. So for instance, it's not so much that we think that humans are bad drivers. In fact, humans tend to be pretty good drivers as long as they're not looking at their phones, as long as they're not tired, and as long as they're not drunk. And so when we look at the kinds of standards that we would like to have for our own self-driving vehicles, human on the best day is pretty much as good as we can get. So here are some photos. This is Uber's car up here, or its car that it's currently fielded for public viewing. And what I wanted to note, it's not really coming through, this is an incredible number of sensors, $64,000 Velodyne on the top, a number of these what are called Velodyne pucks, $8,000 a piece. I mentioned this Drive PX2 compute platform, that's $15,000. So it just costs a lot of money to buy these kinds of sensors. And that's not something that we are really interested in. We could use LiDARs on our cars. If you wanted one of these Velodyne pucks, you'd have a 14 to 16 week delay before you would finally even get one. And then you could start doing research on it. And you would have this closed API. You wouldn't be able to program it to the best of its abilities because Velodyne, the company that makes them, is kind of clinched down on what you can actually do with these sensors. You can't even get raw data from them. So what I mentioned here is that these are massive numbers. We're actually interested in working with more, let's call them mundane sensors, things that you can definitely put on a car and that will likely be what's rolled out on cars in the future. And so there are also a couple of things that I want to point out about the robotic future before I get into my research. I mean, there's a big hullabaloo about what's going on. Last year there was this April Fool's Day joke. It was called the Domino Driver. So here's this little bike kind of thing that's supposed to deliver pizzas. That might sound like a joke, but it's not actually too far away from the future. There are people, like I mentioned, that are already focusing on robotic delivery. And there's another company down here, it's called Moonin, who want to basically automate all of the container ships on the planet. That'd be nice because then you could cut down on piracy and do a lot of efficiency gains in the market. And things that are also in the vein of things where you'd actually, or cases you'd actually need autonomy, are places when, for instance, maybe not Mars and perhaps an asteroid, but down here I picture this one sort of extraterrestrial landscape. So what this is supposed to be focusing on is that there's this planet, Jupiter's here. There's a moon of it called Europa, and NASA would like to send a probe, an unmanned probe, to Europa within the next 20 years. Now, if we were to do that, then Europa is about 30 light minutes away from the Earth. You actually need autonomy in this case. And does anyone know the kind of compute that's actually put on robots that currently go up into space? Anyone have an idea?
68,000.
What?
It's 68,000 in 1985, 68,000 ships.
68,000 what?
I don't know, the 1985 Mac chip, whatever that was.
Oh yes, okay. So basically it's 128 megabytes of RAM, and it's on the order of 20 megahertz processor. And that's actually, if that was what we were limited to, then we'd be completely out of luck. But let's just say that we are willing to send out the kind of computer that we currently are working with in 20 years. That might be a little bit optimistic, but at the same time, we need to be developing algorithms that are quite efficient and are going to be able to get us really good accuracy. And so I've kind of alluded to this so far, but now I'm going to just spell it out. The biggest challenges that are associated with full autonomy are perception, the ability to actually perceive the environment using low-cost sensors, or at least some sensors that we can send up or deploy on any kind of robotic platform. We have the control problem. How are we able to navigate a surface like Europa when it's all icy on that surface and that there might be jagged edges? How do we model the dynamics of some vehicle that are driving on that surface? And then finally, compute, which we can't rely on this. We can't rely on that we're going to be able to have unlimited compute, or that at some point compute will scale such that we can run these algorithms, because frankly, we might not have that kind of chance or a choice in the case of going to these extraterrestrial circumstances. And so I'm going to go over these two different problems, vehicle control and vehicle perception, as they're related to the compute limitation. And so here I give three different examples of really what I would call hard problems when it comes for autonomous vehicles. This is not what Uber is doing when they send their cars out on a sunny day in Pittsburgh. This is not what Google's self-driving car does when it's driving around Mountain View and Arizona, where it never snows. And they can basically just test it only on sunny days. What we're interested in are these cases in which you might lose control of your vehicle. So there's an icy road and you want to be able to detect and respond to the icy road appropriately. What if you're in this situation in which there are dynamic obstacles? So this is a scene in India. How are we possibly going to have self-driving vehicles in a place where we are co-locating our vehicles with bicycles that are actually crowding the streets, and rickshaws and other humans walking around, all acting in a self-optimizing manner? And then finally, what happens when one of the changing models, or a model changes? For instance, we get a flat tire. And so I highlight two graduate students of mine that are helping me on this project, as well as some of our funding agencies that are supporting this. I'm also going to talk about this one problem related to the offline calibration of current sensor systems. So for those of you that work with any perception algorithms, this is actually a really, unfortunately, common occurrence in which you take a robot, no matter how large it is, and you wave it in front of a calibration target in order to determine intrinsics of the lenses, so to be able to figure out how lens distortion comes into play, how spread apart these different sensors are, the cameras and the inertial measurement unit on board. And what happens if, for instance, something bumps and all of a sudden those calibration parameters come out of whack. And also this specular surface situation, again, icy roads being a really great example. Specular surfaces are surfaces that reflect light. So you can imagine a mirror, something is a perfect example of a specular surface. These tend to be sort of challenging because then we can't even determine whether or not it's a surface we're looking at or reflection. So how do we programmatically determine that? And so also two students of mine who have been aiding me on this project, Fernando Nobre and Mike Casper, who will be graduating within the next 2 years, and then some of our funding agencies, including the Department of Commerce. Why are these problems unsolved? Well, we can do as much as we want in simulation. Putting it on a real vehicle is actually really challenging for these, because real life is not this, it is more like this, as we are seeing right now outside. And not only that, but many of these sensor vehicle environment parameters must actually be estimated in real time. So what do I mean by real time? This is a very important consideration. It means, at least in the context of this conversation that I'm having right now, I mean in constant time. That means that if we're willing to do it on our computer, that's fine. That just means the problem can't scale with any parameter that we're trying to estimate, or with any sort of difficulty or challenging situations that we're going to be incurring or applying our algorithms to. So for instance, we need to estimate, I mentioned before, lens intrinsics, some radial distortion parameters, as I'll indicate in a little bit, biases and different kinds of standard deviations of noise on our sensors, as well as vehicle environment parameters, things like any conditions or any kind of parameters related to changing vehicle road conditions. You can think of tire damping parameters, braking force slope as being part of that. And what I mean by this particular area is, if we're operating in any kind of environment, we need to be able to estimate what that parameter, or what that environment is in order to apply control to it. And so I'm going to start by talking about this vehicle control situation. And I'm going to sort of lay out this one abstract, or this one, I should say, kernel of an idea that we would like to solve. Okay, that is that we would like to drive a real car over some terrain park with some challenging features in it. So for instance, there might be a jump as right here, there might be a loop-to-loop. This is obviously not indicative of a real driving scenario, but it's challenging enough such that if we can do driving here, we would like to believe that we can do driving in most other circumstances. And the approach that we're going to take is we're going to capture a model of this terrain park and then determine how a simulated car would drive over it. And then if the car that we're modeling is similar to the car in the real world, then we'll just send those commands that we're calculating on our computer over to the car. And we want to see how that works. Now, there are a lot of concerns that one might have about this approach. For instance, what kind of high-order model do you need in order to simulate real car dynamics? Or maybe, is your car model going to be are perturbations from the car model going to actually approach this real car that you're going to be driving? And as in robotics, I'm going to suggest that let's run an experiment and answer that question through the experiment. Okay. So our approach of using simulation and then loop model predictive control, at first we'll employ a physical simulator, and it'll rapidly model any nonlinear system that we give it. In particular, this high order car model that we wish to model here. And then also we're going to estimate car parameters online, all those different vehicle environment parameters that I had mentioned before. So a quick primer that I should go over is that I mentioned I'm going to scan in the environment, and it turns out that this is an algorithm that's very well known in the computer science community within the past 3 years or so. And what's going on here is one is taking a Microsoft Kinect, and walking it through a room and a series of rooms. And what is being generated is this 3D world environment. This 3D world environment exists in your computer in a scale correct way. And obviously, as shown here, as we're walking through this environment with this sensor, if we have a 3D model, then we can simulate physics in this environment. So you'll see that the example that's being given here is that a bunch of balls are being thrown at this surface. And as the surface is being filled in because the sensor is rolling over it and creating this 3D model, then we can accurately estimate the kinds of behaviors that these 3D balls would have in this environment. We looked at this result and we said, if we can simulate physics of balls, then why don't we try simulating physics of cars? And so this is my little setup. This is our lab environment where we have these sort of quarter pipe features, as well as little half jumps and short jumps and everything, and mostly completely flat. So this is an actual physical lab with these features in it. We've done that algorithm, we've applied that algorithm to data we've collected from Kinect, and we've gone ahead and decided, okay, let's put a car down and tell it where we want it to go. Okay, so we drop these waypoints, and I'm going to explain all of what these different how these different paths are generated. But at least if I start physically simulating the car in this environment and saying, I want you to be able to jump, for instance, and give me some ideas of how you're going to jump, then this is the result. Clearly, we can actually make a car, physically simulate a car jumping over a certain feature.
Is this video on loop, or is this going around and around?
Oh no, this is actually going round and round. I'm not.
It doesn't look like the model's improving as it goes. Like it's the explorations are not converging.
Not converging how?
There's a spread as it looks forward.
Oh, great.
The spread doesn't get less as it goes around.
Okay, so there's currently so you're probably asking about online parameter learning or something.
I thought you said that like a minute ago.
Yes, I did. Okay, and the online parameter learning that we're doing is parameter learning associated with this terrain. Okay, so in this case, what I did was I fixed the parameters. I'm not doing any learning in this example, so I should mention that. And I have some demonstrations later about what some results are for online parameter learning. However, I basically just wanted to show this one example of what's going on. And in particular, I wanted to show these control candidates as they're being generated. So let me quickly show this again. You'll see these lines that are shooting out from the vehicle, right? And this is what's happening here is we're forward simulating the dynamics of the vehicle on the order of about, let's look ahead according to this 0.2 seconds. So just solve the boundary value problem associated with this vehicle to try to regress it towards this red line as planned. And these are the control candidates that are being generated at the order of about 100 hertz, which means that we can generate forward-looking trajectories extremely quickly and also be able to regress them so that we can learn what the correct control candidate would be and then apply that to the vehicle. So at least that should answer part of your question, but not the physical parameters question. Okay. So the problem that's being structured here is, I mentioned, we have a dynamics model of this system. We're trying to solve this series of boundary value problems. Like I mentioned before, we dropped those waypoints, and then we're saying, how do we get from this current waypoint to this next waypoint? And we also have some non-holonomic conditions that might relate to certain kinds of constraints that we have on our vehicle. So just to go through here, we have the system dynamics as modeled. Okay. There's the state of the vehicle, and there's also an environmental parameterization, something like those parameters that we might be trying to estimate online associated with the environment, things like coefficient of friction between the wheels and the ground. All right. We also have that at time t alpha, some time into the future, that we would have a state of the system at waypoint alpha. And I mentioned some constraints, e.g. from the actuator, So you can't turn that quickly on a car, and you can't express those conditions necessarily as this vector field, so we need to have some of these sort of non-holonomic conditions. All right, so there are some challenges associated with this, and I want to be upfront and be very clear about it, because as with all methods in robotics, the hope is that this works, and there are cases in which it doesn't, and we should be clear. So F is nonlinear, very high order. We basically are deciding to model this as high order as we want. If we choose T alpha in a certain way, this boundary value problem may not have a solution, which means that we'll be doing some sort of regression problem on, we'll do a regression algorithm on a problem that has no solution. Also, these generally require some sophisticated numerics, which would result in non-real-time behavior. So that's obviously a problem, and we need to address that directly. There are no stability results on solutions like this if we are using a numerical solver, and that means that the solution may not be self-correcting. If you are slightly off from the reference trajectory, then you could drift away from it for a long time. And finally, how does one estimate this theta of x, which Andy Arena just mentioned, I believe. So
That's my name.
yeah. Okay. So first, we create the reference trajectory, which I've referred to a few times already. We drop these waypoints. We say that at each waypoint, we are going to satisfy some pose, which is x, y, z, roll, pitch, yaw, okay, velocity, and also a curvature constraint that's related to essentially how the wheels are turning at that one waypoint. And this can be solved by employing this physics simulator, as I mentioned before. So assume that you have some waypoint of your vehicle, x sub I, and that you're trying to get to this next waypoint, x sub f. We employ the physics simulator, sorry, in order to forward project dynamics over a certain time length. And what we might end up with is some trajectory that does not exactly line up or get us to this x sub f. Okay. So what do? We use optimization on this problem. So we're trying to drive e sub b to 0, and we set up this residual. This box minus operator is related to an SE3 pose difference. So note that in XYZ, it's just going to be a difference between the degrees of freedom, x, y, z, iteratively. But if you're trying to take a difference between roll, pitch, yaw, then that requires some more sophisticated handling. And for each waypoint L, we're going to solve, quote unquote, this boundary value problem via parameterized curve, which I'll explain in one moment. And then we're going to minimize this e sub b. Okay, so we're setting up an algorithm that hopefully will get us to get correct control inputs C in order to solve this problem, with everything else being constant. All right, now
So what are you using as the boundary value solver?
So in this case, what we're doing, so the boundary value solver is actually a forward projection of dynamics in time, and then Gauss-Newton optimization on this residual E sub b, using over as a parameter optimization set some parameterization for the control signal. And in this case, we use Bezier curves. So if we use fifth order Bezier curves in space and in velocity, then we can actually fully define all of our angles associated with the rigid body motion and solve this problem in only a 5-dimensional space, which is a lot easier than trying to solve the finite difference problem associated with this. And so the result of why we use Bezier curves, we tested out a bunch of different curves. Spline curves, for instance, result in too high of curvatures in the curve, and so we went to Bezier curves because they sort of demand that there's going to be a nice smooth curvature change with minimum curvature. We can actually explicitly say that certain kinds of maximum curvature bounds exist on a Bezier curve, so it turned out that that was sufficient. Other people use Dubin's paths and everything else in order to solve these sort of non-holonomic vehicle problems.
And can control signal steer angle?
Yes. Okay.
So it's one
So I should mention there are two inputs that we have to the system, right? With any car, then we can steer it, and we can put our foot on the gas. We can also brake, but I'm ignoring that for now. Okay. So those are the two kinds of control inputs that we have: voltage across the motor, and then turning rate or turning angle. Okay. So we can solve this problem also in multi-threaded fashion. Basically, you can do this integration of dynamics on each degree of freedom for the optimization. So this control signal, as I mentioned before, is now parameterized according to some p value, so just a number. And we can, for each different number, run a physical simulation and use finite differences in order to calculate a Jacobian and invert that in the end in order to solve for that optimization problem, which is exactly what we do. Okay. Now, this is the actual car. I just threw the picture in here because I wanted to show you that we built this car, and this is the car we're going to be testing with in a second. There's also another aspect of this problem, though, that I haven't talked about. All I've mentioned so far is that we are planning the reference trajectory of the vehicle. But once we have that reference trajectory, we know we will drift from it in time. That's the problem with control theory, right? We're trying to actually stabilize to a trajectory that we know exists, or this reference signal, as I mentioned before. And so we set up this control problem such that we're trying to move our vehicle to this reference trajectory, but over time, future time horizons are going to be downweighted, and mostly we're going to be looking at this error in tracking this trajectory as it's temporally relevant, the moment that we're in right here. Okay. So we set up this other residual that's associated with trying to minimize the control problem, which was what was being solved by those candidates that were being shot out from the vehicle before. Okay. And like I said, we can solve this problem at 100 hertz. Turns out we only need to solve the other problem once in order to generate that reference trajectory, as long as the vehicle parameters aren't changing. Okay. So moving right along, I want to show you what this looks like when we actually put it on the vehicle. Because all I've done so far is sort of demonstrate to you that, okay, we can go ahead and apply or calculate these different reference trajectories, as is going to be shown on this software cutout right here. Here's the reference trajectory. Here's the vehicle with state feedback being provided by a motion capture system in our lab. And essentially these control signals are following this reference trajectory and being calculated at a very fast rate, such that state feedback is immediately being included in the system. All right. And so at least in accomplishing something simple like jumping, this might sound kind of uninteresting, right? Well, at least for that low jump. For the high jump, we have a different story. So what we've done is we've placed a waypoint on one jump over here, and then this other jump right there. So a human operator might be able to land this vehicle without crashing it. A human operator is less likely to be able to actually land on this opposing jump repeatedly. And so this is the kind of behavior that we'd like to see, and we're kind of happy about it. One thing that is actually not present in this video that I can actually show it to you afterwards is there's some audio with this video. You can hear that on this vehicle, the rear wheels are spinning as it's landing in order to stabilize it so that it's pitch up as it's landing and the rear wheels fall first. And that is not some sort of behavior that we programmed in. That's actually what the physical simulator is telling us we must do in order for us to stabilize the landing. And so this is sort of the last segment of this one little video right here. And as we go through this loop, okay, it can go through a loop. Well, you know, maybe a human operator could do that. Let's look at the front wheels as it's going through the loop. You'll see that there's a massive stabilization that occurs that is generally outside of the realm of maybe a PID controller would give us. And certainly it's operating in a fast way. So we know that at least this method appears to work. Now, I should also mention one thing, that the state feedback was provided in that video by these cameras, what I called motion capture before. The motion capture obviously loses tracking as it's going upside down, and in parts when it's airborne. And so there's also an inertial measurement unit on this vehicle, and we're forward integrating those measurements coming out of it, which is going to be the topic of my next section. But at least for now, this is the control problem as we're solving it, and we're looking forward to new ways of explaining this as it relates to real vehicles. I realized that I did not talk more about online parameter estimation, so I should talk to you more about that later if you like. So sorry about that. All right, so here are some takeaways that we have about that project and things that we want to look at in the future. So first of all, complex models, they can be used to aid sort of practical behavior, things about landing or sort of skidding. The car was skidding in certain cases in that video. And those models allow us to actually determine how that behavior will affect our vehicle and then send appropriate control signals to it. I also mentioned learning for parameters can be done. Something that I didn't mention at all so far is that we had to tune that model that we had, and we, in some cases, had to run the car and then use state feedback and do this optimization. I'm very concerned about that method, and this is the kind of method that's being employed by many real car companies right now. They drive their car and they empirically determine a parameter such as maybe the spring coefficient that's on their vehicle. I think that's dangerous because what that means is that we're opening ourselves up to overfitting, and we need to be very careful about that. Okay, the third thing is for vehicles, some model uncertainties are addressable by state feedback. That is to say, we know we're not modeling the full behavior, the full dynamics of this vehicle, and at the same time, we still can drive the vehicle through these different cases. And so state feedback, I think, is helping us a lot there. And so future directions, there are these different kinds of driver assists that exist. So ABS is one of them, and then sort of electronic sort of steering is another one, or electronic stability, as it's called by some vendors. These are systems that are generally black box systems. So for instance, we do work in part with Toyota, and what they tell us is, some of these systems are given to them, and then they must characterize them in some way, but they're not necessarily given the guiding behavior of these systems. We want to be able to model those systems and then put them on our vehicles so that we can appropriately do planning with them. And then I also mentioned sort of black box engine models, and as well as granular materials or other kinds of more complicated physical scenarios in which we might be driving. Now I want to switch gears and talk about this second difficult problem in self-driving, which is vehicle perception. So vehicle perception is actually the driving difficulty, in my opinion, behind most autonomy. It's the ability for one to relevantly make decisions or relevantly collect data and make decisions based on it from a suite of different sensors. And that is a very general problem. I mean, that's the problem that ranges from being able to look at a police officer with his hand out, and infer that means that you're supposed to stop, something that's generally considered a nearly artificial intelligence level problem, although deep learning's gone a long way to try to solve it. The second kind of issue is related to how these sensors even react with respect to one another so that you can know where you are. And so that's one that I'm going to be talking about in depth today. So this vehicle that's being run through this calibration process that is looped in this case, there are 3 different cameras on it, and then there's this inertial measurement unit. And to talk a little bit about how we would be able to do navigation, I draw this graph here. Okay, so this is a relationship between cameras that are sitting on some vehicle or a robot, and a calibration set of calibration parameters here that determine the offset between, let's say, this camera and then an inertial measurement unit. So this is an accelerometer and gyroscope again. What it does is it gives us data that we can use and integrate in order to get motion estimates. Now, typically what happens is, as a camera is moving through a scene, then what will happen is you sort of detect that there are some points in the scene, and then you're able to project those into the camera plane, and from there determine where these world points are, things like corners in the world. Okay, but the IMU, as it's mounted rigidly to a robot, that's also going to be giving you these accelerometer and gyroscope measurements, which in part are supposed to be giving you the exact same information as this camera, offset by this transform here. So this transform typically is rigid. So that is to say the camera and IMU are rigidly mounted with respect to one another, and that they're not going to change position. But I can automatically tell you that sometimes very often that's not the case in long-term autonomy, and sometimes it's designed not to be the case. For instance, if you have a camera attached to a robotic arm and you're moving the arm while you're also moving a robot, that would be a particular case in which this is time varying. So it appears that the estimation of this particular parameter here is something that needs to be done in a more long-term way, more robust to changes as we're operating a robot or a self-driving vehicle. And in fact, both of these sensors are on a self-driving vehicle and anyone that's going to be fielded in the future, it appears. So this is quite relevant to the actual operation of these cars. So we want to allow for these sensors parameters to change while operating the vehicle without losing tracking or losing an idea of where we are in a scene. And so our approach is that we will do online estimation of this transform using naturally occurring features and drawing on the most salient time series of motion samples. That is to say, we will be able to take large amounts of data with these sensors. And from that time series of data, we're going to cherry pick the best sequences for estimating what those parameters are. So here are some different motivations of why this would happen. I mean, there will always be erroneous driving, even when we have some sort of computers driving these cars. Okay? And if you end up slightly jostling the chassis of a vehicle, then you cannot assume that the parameters of those sensors on those vehicles will remain the same. Not only that, but if they were, what would happen? Let's say that you decided, okay, my sensors are out of whack, and I'm going to go ahead and just stop the car. Sometimes stopping the car is not an option. You could be on a highway, you could be in the middle of nowhere, and so there needs to be some sort of system that actually recalibrates these sensors as you're going. And so these are two examples. I mean, I just showed you this video, and I can tell you that through this jumping procedure, there are portions of this vehicle that are going to be jostled and moved around. And even a millimeter of inaccuracy on a sensor rig, when that is propagated all the way out into some features in the scene, that'll result in a massive error in terms of the state estimation for the vehicle, for instance. And then there's this other example, which one of my graduate students here is taking a camera and then moving where the camera is on the robot itself. And I'm going to get back to this video in just a second. So some goals. We want to be able to develop power on and go operation. This is sort of the key of all robotics right now, that we would not be setting up these situations in which everything is perfectly done and then all of a sudden we're ready to run our experiment. It only runs once and then we can never recreate it. We want to be able to avoid that kind of problem while also accomplishing the solution or obtaining the solution to this simultaneous localization and mapping problem. All right, so I also mentioned that we want it to be robust to intentional and accidental changes. We want to be able to easily add and remove sensors from an algorithm like this. And then finally, the biggest set of parameters that we would like to estimate are these 6DOF transform that's associated with the rotation and translational offset of cameras and the inertial measurement unit. So, really briefly, I'm going to talk about these two sensors. One, cameras give you relative pose constraints. That is to say, we're going to be able to look at where a robot is in one frame, slightly move, and then be able to determine where it is in another frame based on the motion of certain objects that are within the field of view. And it gives you some information on structure. That is to say, we know where these desks are because we're able to look at the corner of this desk and notice that the perspective of this desk is changing when you have a set of two cameras, for instance. So IMUs, on the other hand, what they give you are these strong short-term spatiotemporal constraints. Why is it short-term? Because IMUs tend to be extremely noisy, even very expensive ones. So while cameras are extremely repeatable and there's a wealth of data, IMU, on the other hand, gives you sort of noisy data, but gets you through these portions in which you're losing tracking. So let's say that it were dark in some area of the scene, or maybe you were looking at a white wall. Cameras can't really tell you much there, but IMUs at least can. Okay, and I give this example here, or this graph here, to show you exactly what it is we're estimating. So assume that there's some sort of feature in a 3D world. So for instance, corners are very effective features. And when that feature is projected into the camera plane, then if we were to move the camera a little bit, then we would be able to determine how the camera has moved simply because we know we're looking at the same feature, right? IMUs, on the other hand, you would integrate along this path, and then this would be the exact output of your IMU, and then you'd be able to determine, okay, this is some motion estimate. But now there's this T sub PC, which is the transform between the camera and this one point that the IMU is at right there. That is what is to be estimated. And so we can see that there's a bunch of relationships saying that, well, this transform here should be equal to this transform here if we apply this T sub PC to it. And that is how we're going to end up estimating that particular quantity. So some notes again. This implementation must be real time. We're going to be using some adaptive conditioning, that is the ability for us to change the length over which, or the time series over which we're going to be doing this online estimation. And we're going to be using some visual features in order for us to estimate the motion of the camera over time. So I mentioned right here, I mentioned before this corner tracking. And what does this look like in real life? This is a smartphone, no more complicated than a smartphone. And what we're doing is we're tracking these different corners in the scene. This is some algorithm, or this is some software that we wrote in my lab. Basically, we're estimating the motion of these corners in time. And with each iteration of time, then we can determine how we've moved with respect to the previous frame by looking at these tracks, what are known as feature tracks. And on the right-hand side, I'm going to show you this again. We show these 3D world points that we're estimating over here, these boxes, show up as white dots on the right-hand side. And then these coordinate systems, these red, green, and blue lines that are orthogonal to one another, they represent the estimated motion as we're moving through this scene. Okay, so you can clearly see that this sort of algorithm works fairly well and is pretty common in robotics, just for mapping out something like this corridor. So you can even see the structure of the corridor here, and as you can see, there's also some noise that we need to be able to consider and handle in our algorithm. All right, and so finally, I mentioned again, we're going to be doing an online self-calibration of these extrinsics. How does this end up working in our practical world? So imagine you have 3 different estimated positions with respect to one another. And there's this candidate segment over which you're going to be estimating some parameter for those T sub PCs, as I mentioned before, the offset between your camera and your IMU. And from that estimation, you will end up with this number where you assume the parameters to be at, but you'll also get this covariance for this multivariate Gaussian distribution of the of the measurements that you've taken. And so let's just say, okay, well, that's one possible set of parameters that it could be at, but it's somewhat noisy, so there's some covariance associated with that distribution. Now you add another pose. You take the very next motion, and then you say, this is a new candidate segment, and now it's estimating some perhaps different mean, but with a wider covariance. And that can just be naturally occurring based on, say, fewer features that have been tracked. And so you go ahead and you throw that into a queue as well, and you say, well, this is one estimate, this is another estimate. And you go and you iterate forward in this fashion. This next segment is going to give you a different estimation with a different covariance. So the way that this works in terms of capturing informative segments is we're doing a constant comparison between the current candidate segment that we have and all of the other different segments that we have in the priority queue. This priority queue represents, again, those time sequences in which we've been doing estimation of parameters for this camera to IMU offset. And so in this case, what has occurred is that this candidate segment says some mean, and now it's going to be a slightly narrower covariance. That is to say, we are more confident in this measurement that we've just made. And that just kicks the lower confidence estimate out of the priority queue. So you're constantly strengthening this priority queue as you go, and therefore getting a better estimate of what your parameters are. And so this continues to go. This one's rejected because not any narrower than these distributions, and so this goes. Okay, this one also rejected. And so as we move forward, then this is another example. We would be having these poses being estimated based on these landmarks. And we are not only doing estimation on the parameters that I mentioned before, but we're also doing estimation on our positions and the positions of these landmarks. It's kind of, it's nearly unbelievable that one can estimate all these different features at once, but as it happens with the different sensors that are coming into play, it is possible. And the way that this remains real time, which is really the kicker here, is that as we're doing the estimation, we're no longer doing optimization through this entire graph. Okay? Instead, what we're doing is we're optimizing over some sliding window here. Notice that this sliding window is completely separate from the candidate window, except that they both are operating at the leading edge. And so this candidate window, as I was mentioning before, is used to estimate those parameters. The sliding window, on the other hand, estimates the position and landmarks of your vehicle. Okay. And so this is another representation of what this looks like. You can have different disjoint priority queue segments, and each one of them contributes to your understanding of what the calibration parameters are. And on the other hand, you're always testing against this candidate segment that's at the leading edge. That is to say, we're taking new information in, and we want to determine whether or not this is a better estimate for what our calibration parameters are. And now you can see that this is a pretty full algorithm associated with trying to estimate both parameters for the system as well as motion of the vehicle. Okay, so now I'm going to talk about what happens when calibration parameters change. Notice we haven't really talked about that yet. We've just talked about when you get different informative segments. So now let's say that we get a new candidate segment, as I mentioned before. And this is our current priority queue of segments. So these all have means associated with them that are close to one another. Perhaps the covariances are different. And what we do is every time we collect a new candidate segment, we're going to run it through a hypothesis test. Okay. This test asks the question, what is the likelihood that this new candidate segment represents the same mean as these candidate segments down here that are within the priority queue? And notice this hypothesis test is becoming strengthened with even more segments down here that are being added to the priority queue. And so this hypothesis test asks the question, do we have a 10% likelihood that this candidate segment could be part of the same set of parameters down here? And if not, then, if it is, this is actually incorrect, okay? So if the hypothesis is false and they're not equal, then we must clear the entire queue and use these new parameters. So practically speaking, what this does is it says, okay, this new candidate segment has come in. We have a new estimate of the parameters for our self-calibrating rig, and that is significantly different than what we thought they were before. And what does that mean? That means that all of these segments down here are worthless, because they're all saying that the candidates, or sorry, the parameters for the rig are set A, and now we believe we're in set B. So we clear the entire queue and start collecting new data. And this is what allows us to do self-calibration. All right. There's a quick caveat here. It's that when one is trying to figure out the difference between two rotations, one does not simply subtract two rotation matrices, of course. We in fact need to sort of lift this to a tangent space, and then we use an adjoint operator based on the original SO3 manifold in order to subtract the two. And that's the space in which we're doing optimization. So that's what I draw here. And so notice that I also said we're conditioning on sliding window for new for past poses. And what happens when these new measurements come in that say that we have a change? All right. So in that case, what we're going to need to do is reapply the parameters that we've estimated in the current candidate segment to those poses that were being estimated for position before. So this is sort of a post-hoc repair mechanism in order to make sure that the continuity of the graph remains the same. And the way that we determine that, we go back through each single pose and then we say, test whether or not the confidence interval around this one measurement is within 2 standard deviations of the measurement we expected it to be. If it is different, then apply the new set of parameters to it. And so this is the final slide of graphs that I have to show you. And essentially what is going on is here are the inactive poses over which we've set the values and we're no longer caring about what they are. On the other hand, these new poses, positions and orientations, are what we are going to be doing some amount of fusion into the current optimization for. And then you have these series of windows. This conditioning window that can change in size, that looks back and says, should I expand this window in order to do the estimation? And then also different candidate windows that are being thrown into the priority queue. This can be done for different sensors. So what Toyota is most interested in is what happens if I want to add another camera. Well, the case goes that you can add some new sensor, we initialize it, and then we build our cost function in order to do the minimization of error on the pose graph. And then there's a different priority queue for each of the different sensors that you add in. And so here's an example of an outdoor test of this. So here we have some change event. What's happened is Fernando's gone and he's moved the camera from one position to another on the mast of this one robot. Okay. And what you'll see here is that there's this change in values of the rig. So here, this black line is the ground truth parameter. So you'll notice that what's happened is that Fernando's gone and moved this sensor by about 0.2 meters here, about 20 centimeters. And so this black line has gone up, and then the blue line is the current estimate for those parameters in time. And then the red line is sort of the confidence interval for it. You'll notice that even throughout this, there are no other kinds of changes that were noticed. So Fernando just moved along one axis. And so here's the experiment. Okay, so we're operating outdoors. Here's the same showing of, or image of features as they're being tracked in time. And then on the right-hand side is that 3D landmark and pose graph that I was talking about before. All right. On the left, you see these green lines, which are the instantaneous sort of candidate segments that would be applied if one thought that these were the actual parameters of the rig. And then the red line is the estimate, the current applied estimate. And so here's just a video of the robot moving outside. And so we're just rescaling on the left, and we're building the pose graph up here. Notice that actually moving this robot in front of one of those targets would be quite challenging. Moving a large car is impossible. So here, Fernando's gone ahead and moved those camera on this rig. And what's happened here is that there's a repair of the pose graph as mentioned. Down here, there are re-estimated parameters in time. And so this is the new set of parameters which have been applied, and therefore they're now being used in order to do simultaneous localization and mapping on this robot. And so what's going to happen is we're going to complete this loop in just a second, and or maybe I guess that was we didn't complete the loop completely, but we drove all the way around, and the pose graph ended up basically on itself, which means that we completed the loop that we expected. And so that's the implementation sort of details of this one example here. All right, so where do we want to go with this? We want to be able to do online parameter estimation, not only of the rig, but also of the environment around us. So over here, I show this one video showing that we can actually estimate the position of lighting in this one scene and then regenerate the scene itself here. And this is something that we would like to introduce into the pipeline in order to say, we can actually go ahead and now know where light is coming from and how light is reflecting in this scene in order to determine things like whether or not there's going to be reflective surfaces in here. And so with that, I will show this blooper reel, I hope. Oh no! 1 second, let me figure out. Okay. Well, that's really sad. I wanted to show that because basically we had a time series of people trying to drive this vehicle through the loop and obviously just failing miserably. But let me see if I can bring it up. But that's all I had prepared for slides. So thank you for listening.
Thank you, Chris. Any questions?
Yeah.
So, do you ever think about control for calibration? So if you can take control actions because you want to achieve some goal, or you can take control actions because you know that your sensors are wrong, and if you just look over to the side, there's a really good landmark that might help you figure out how your sensor has been bumped off course.
Yes, this joint optimization problem is one that I think is very interesting, and it's interesting in two ways. The first way is that very few people do this control perception feedback right now, and that's not to say nobody does, but it's a little bit rarer in the community of robotics.
Which exactly is that?
So what was being mentioned was whether or not you can choose to control your vehicle such that some parameters are more observable, for instance, I believe. Okay, and so first of all, there's a team at USC that's basically asking the question, can we get good scores on our confidence on some of these parameters, which is already kind of an interesting question, whether or not a parameter is observable and how you know it's not or it is requires some knowledge of the noise profile and uncertainties. The second question is, can we suggest good motions to an operator or a control sequence such that we will be able to find what those parameters truly are, right? And I will say that yes, we are operating on that. We are working on that problem right now. Essentially, we're starting with the most naive approach, right? We say the covariance on one parameter is so high, and what does that mean realistically for our system? And can we impose a certain kind of motion such that we will drop the covariance or the uncertainty on that one parameter? But that's I mean, in some cases that's quite hard. For instance, you don't want to roll a vehicle, right? So trying to render that parameter observable might be quite challenging. And yeah, we are still working with how that might be possible. Yeah, Alex?
So in the first part of the talk, where you were selecting your waypoints and solving the two-point boundary value problem, did you ever have to adjust the distance between the waypoints to make the problem simpler so that
Yes.
you find a viable control?
Yeah, and I mean, again, I try to be as honest as possible here. We did have to adjust those parameters or the position of those waypoints because this is not a global planning algorithm. The global planner is you, the human, dropping waypoints, right? A better approach to this would be that you would use something like an RRT, PRM, or any one of these rapidly exploring random tree or stochastic search approaches in order to drop where those waypoints are between a start position and a goal position somewhere far away. Or maybe you would say, I want to go in a loop around this. But then, you know, questions about how you would bias a solver for instance, a global planner to jump through a hoop or something like that. I mean, it will almost always be energetically less preferred. You know, it'll almost always be time less preferred. So we can't really demonstrate that the local planner would work. Although I will speak a little bit to this. We are currently implementing something like RRTX from Michael Odie, which I mentioned to you earlier, in order to do sort of dynamic replanning in the presence of dynamic obstacles, which is something we're very interested in too for real vehicles. Yeah.
And how in general do you deal with constraints? If you have situations in which your description of the problem involves more coordinates than the minimal numbers that are necessary to specify a state of the system because there are constraints that are satisfied. Do you try to find the minimal set of coordinates, or do you just deal with the fact that you're using everything that you measure?
Yes, that latter. So minimal sets of coordinates would at least allow us to avoid some of these overfitting problems, especially not only in solving boundary value problems, but also in the parameters of the system that we're modeling. I can say that right now, all we've done is this is the kind of approach that we've taken to it. Use this simple car model. If simple car model is not enough, try to simulate new physical phenomena. replan, and then determine whether or not you've fallen off the path. And that might sound very much like an industry approach, which I will shamelessly say I hope that it gets us closer to a real solution of the problem, but we are sort of moving further and further away from the principled approaches that I think we should be tackling. This, I think, speaks greater to, this might be ambitious of me to say, but I think it speaks more to that we are results-driven right now than rigor-driven. And that's something that I have seen industry push and NSF push back on. And so I'm hoping, like I mentioned earlier today, that we recently won this NSF CPS award that is basically adding rigor to real card control. And I would call this closer to real card control. And now we're trying to put formal verifications on those sorts of systems, which will involve in part trying to distill down the state space and the number of parameters, or using some sort of other, bumped parameterization, for instance. And that is something I'm very excited about.
Can I just
Yeah.
just ask this question again, or maybe ask the question again? You have pitch dynamics in flight in your car, and you said it discovered this revving the engine to control the pitch, but presumably you did not have pitch dynamics when it was driving around on the ground, or you do have
No, we
pitch
did. Yeah.
So even though, okay, so your car has suspension all the time.
So, yes, it has suspension
So
all the
it's not turning
time.
constraints on and off, really.
No. But what I want to say is that we do have an indicator that would say, you could be airborne right now. Which then basically tells the car tells the solver to say, you can do whatever is necessary and stop doing as many control control candidates. So there is this weighted difference between whether or not we're trying to immediately drive towards our reference trajectory, and there's very little controllability that you have on this vehicle right now, and don't even search the space of control candidates that would be trying to impart some lateral motion or something like that.
So you hand put in that switch. It's not
That airborne switch, yes. Yeah. But nothing about pitch, like telling it to pitch control in a certain direction.
Yeah, but usually people wouldn't put the angular momentum of the wheels into the model at all.
Yeah, it's true.
So you have to add that.
We had to, yeah. It's a good question. You know what happened when I first showed Toyota that video? Do you want to guess?
They said that you cheated on the ramp to make the pitch dynamics work.
No, they didn't say that. It's actually much simpler than that. I don't think we cheated on the ramp, but I suppose it could be debatable. Cheating is very common in robotics from different perspectives, right? But what they first said is, we don't want our car to jump, so why are you showing us this video? To which I had no response. Well, I guess we shouldn't have shown you that video. We should have driven it on ice, but we just spent 2 months doing this video, and oh no, right? But the next video will be on ice and not a jump, and maybe then you can talk more saliently about things they're interested in.
Any more questions? We're going to have a chance to speak personally to the speaker next door and have some refreshments. And let's thank him again.